What two energies you have seen so far? Kinetic energy and potential energy. Kinetic energy is due to motion. If the object is at rest, does it have a kinetic energy? No, because it has to do with motion. It has to be moving for the object to have the kinetic energy. And in fact, it varies with the square of the speed. If the object is moving, kinetic energy is changing non-linearly with the speed. It increases more. The other energy, potential energy, that is related to the position. If I move one thing from one position to another position, I'm actually changing its potential energy. Correct? Potential energy is the energy stored in the object if the work has been done on any object. So whatever work you do on the object, that is stored as its potential energy, which can be used later in some other form of energy. Correct? There were two formulas that are introduced for kinetic energy and potential energy. Kinetic energy is equal to half mv square, right? Potential energy is related to, so we worked with the potential energy due to gravitation, correct? When the object is under the effect of gravity, and this is equal to mgh, right? That's the formula for gravitational potential energy. Okay, there are other kinds. We will do one more kind in addition to the gravitational potential energy, but that is the starting, that is the introduction of potential energy, how the potential energy varies when the only force acting on the object is the gravitational force. Also, on our way, we derived a formula which says delta KE should be equal to the net work done. What is this called? Does anyone remember? There is work on one side and there is kinetic energy on the other side. What is it called? It's a theorem. And that's what we will use all the time solving the problems. Work energy theorem. That means if the whatever is the net work done on the object, that is equal to the change in kinetic energy that results in changing the kinetic energy. So if you have applied force on any object and it does some displacement under it, there will be the change in kinetic energy involved. That is the work energy theorem. That is the theorem that we will finally establish it using adding these energies to this theorem. Now, W net is equal to, this is also something that we have seen in previous lecture, delta KE. W net can be written as WC plus W NC delta KE. Do you remember what are WC? I didn't hear. Yes. The work done by the conservative forces, the work done by the non-conservative forces. What are the conservative forces? Is gravity a conservative force? Yes. Example of non-conservative force? Friction. The whatever work has been done against friction, that cannot be recovered. That is mostly that is gone in the form of heat. Now, so far, if the work done by the non-conservative, if we are, let's say, we always start with the simplest case where the friction is not there, it's zero, but we know ideally friction should not be there, but in real life friction will always be there. So in simple cases, when there is no non-conservative forces, if the work done by them is zero, then this equation becomes WC equal to delta KE. Correct? Make sense? So, and now this is where we ended our last lecture. If you look over your notes, you might be able to find delta PE minus is equal to W, right? That's where we ended the lecture, last lecture, where we came up with the formula for potential energy due to the gravity. And before that, we were finding the work done by the gravity when the object is moving above or away from the gravity or towards the gravity. Why it is negative? Because it is decreasing potential energy when the object moves in the direction of force. Potential energy decreases. So when you are moving something up against the gravity, potential energy is increasing. You let it go, it falls, potential energy is decreasing because now it's moving in the direction of gravity. Good so far? Now, you just said that the gravity is the conservative force. So that means I can, if this is my force acting on it, and I replace that here, minus delta P E G is equal to delta K E bringing them on same side, delta K E plus delta P E G is equal to 0, right? If I, because they both are the change, right? So I can take this delta outside, Ke plus Peg is equal to 0. Make sense? Right? So I have not done anything yet where I have introduced something new. I'm still playing with the same numbers, trying to come up with a final equation which represents the total energy of the system. This, what is this? Kinetic energy? What's that? Potential energy? What does this equation mean? Can someone tell me? No. Yes. Change in total energy is 0. Or the other way to say it, energy is constant throughout. Total energy of the system remains the same. What is this called? Law of conservation of energy. Have you ever heard of it? Law of conservation of energy is valid in under all conditions. That tells you energy cannot be created or destroyed. Okay, it can change its form. It can go from one form to another form, but the total energy of the system remains constant. So if I replace this by delta E total, that is 0. That is the law of conservation of energy. All right? Or I can also write it as what Kala said, that the energy remains the same, E, kinetic energy, Ke plus Peg initially is equal to Ke plus Peg finally. You all understand that why I'm putting G under it. Why there is a G? Because it's due to gravity, okay? It's important in a way because we're going to introduce another kind today. So initially, whatever is the kinetic energy of the system, now system may comprise of one object, system may comprise of two objects, but total energy of the system The law of conservation of energy says the total energy of system, or let me put it isolated system. Isolated system means there is no external force acting on it. Always remains constant. Yes. Isolated system always remain constant. Isolated system, no external force is acting. Do you need to have, so there's one important point I'm going to make here about the reference point. In order to define the kinetic energy of any object, so if I am defining the kinetic energy of the car, do I have to define it from where it started, from some sort of reference with respect to Earth, with respect to Moon? Do I need to do that? No. If you just know the speed of the car, you plug in the formula, it does give you the kinetic energy of the system. This is not true for potential energy. Potential energy is always defined because it's related to the position. It's always defined with respect to a reference. Okay? Because of its definition, this is always defined with respect to a reference point. What does that really mean? So if I move, so when we define the potential energy, for example, if I'm trying to define the potential energy of this book with respect to the floor, can someone tell me what is that going to be? What information do I need to find that? If it is with respect to the floor. Sorry?
The mass of the book.
Mass of the book. I already know gravity. What else? The height of the book. Correct? If I have that information, I would have the potential energy of this book. What if I define it with respect to the table? Sorry? No. If I want to know the potential energy of the book with respect to the table. And what height? Huh? 0. That would be 0. Is that right? So potential energy with respect to table is 0. With respect to floor, it's not 0. All right? If I take ceiling as a reference, right, what do I need to know for this potential energy of this book? Whatever is the distance from the ceiling to the book, right, and it's going to be negative, times gravity again and its mass. So my reference line can change the potential energy. Okay, potential energy could be different with respect to the reference point. You can think of it the same way, like position of Samantha with respect to me is not same as the observed by the observer sitting over there. Okay, because we both are looking at from a different point. So the reference point can change. Potential energy does depend on it with respect to the reference. But how do we compare then different changes? The thing is, change always remains constant, no matter whatever is your reference point. Delta PE always remain the same. Okay, it really does not matter which reference point you take, all right? The potential energy value could be different, okay, positive, negative, depending on the reference point, but delta P remains constant, and that's what we are interested in. That's what most of the time we are interested in finding, and so the total energy would still be, it will always lead you to this formula that the total energy would be constant, even though you can use a different reference points. Let's quickly do a problem related to it. How can we see, or how can we check that the reference point using the change in potential energy, where does this energy go, and how do we apply this law of conservation of energy formula here? So there is my favorite, a roller coaster. Have you all been to a roller coaster? Survived? Of course, we did. I hate it. It's horrible. Upside down, so fast, going backward. I never thought I'll come out of it alive. So it is sitting on curved surface. The track, you may think of the part of the track. You are starting from, it is starting from the height of 40 meter with respect to this reference line. Okay. Now, you could have taken its initial position as the reference point. There was absolutely no problem with that. There is position 1, and then there is position 2 when it comes down to this point. Are we good? The problem, we are setting our reference point at here, it's 0. Initially, yi 0. So what that means, that's my 0 line. That's where I would be taking all my positions. Oh, no. Let's keep this. We can do that, but it's going to bring, so I will start with Vi 0 here, and Vi 40, this is the Y is 40 meter here. And let's not call them anything, because I'm going to use them in the equation. And I'll tell you, once I start, I'll tell you why I don't want to give them any symbols yet. All right, that's the initial position. Initial velocity is 0. It starts from rest. That's given to you. You want to know what is the final velocity at this point. Good? So what do you think? What comes to your mind? How I should start? There are two positions, one position, two position. There should be some energy at the top position. There should be some energy at the bottom position. What is true for both positions? Is kinetic energy same at position 1 and 2? Say it again.
No, because it started left.
Yes. So it's not the same. Initially it's 0 and then it will reach up to some value. Is potential energy the same for both? Is potential energy at the highest position is same as the potential energy at the lowest position? No. Which one has more? The top one. Correct? All right, we all agree. But how do I start the problem? I don't have any reference. What should I do? What information do I already know about both positions? By default, total energy is the same for both. Is that right? Whatever the total energy here, kinetic energy plus potential energy, whatever the total energy here, kinetic energy plus potential energy, they both should be the same, right? Because law of conservation of energy, total energy of the system always remain constant. So energy at 1 must be equal to energy at 2. Remember, my reference line is here. So this is my 0 line. This is my reference line. Okay, I'm taking, so whatever, if when you are here, it's 0. When you are here, it's 40. Okay. So energy at 1. Can someone help me write what energies I should take for 1? Initially, or what energy I should be dealing with?
You should solve for
Kinetic. Right? Good. I just take the formula. I wrote the formula for that position. Initially, whatever the numbers are. And what's the energy at 2? Half m Vf square plus m g yf at 2. Good so far? Now time to plug in the numbers. What is that? 0, because initially speed is 0. Good. 0 plus, how about this? That's not 0, right? I think I'm going to have to give you the mass for the roller coaster. Let's keep it the way it is. And yi, 40. Good. Equal to half m v f square. What about this? Because it has reached to the reference line. So that is the potential energy at this point right on the reference line. So yf, now I am adding it. Yf is 0, yi is 40 meter. 0. Okay, because it has reached the reference line, right at the reference point, potential energy should be 0. Now, I think we're not going to need mass. Half m v square, m gets cancelled. See, you might think initially, you might think that the mass was needed, but mass got cancelled on its way. G times 40, you can further solve it. Solve for Vf. Tell me what number you get. Hmm? 28 meter per second. in one line explanation. Initially, it only has the potential energy. All the total energy is its potential energy. When it starts to move, it speeds up, it's converting its potential energy into kinetic energy, going down. When it reaches to the bottom level, all the kinetic energy is coming from starting its PE. Somewhere in the middle is PE plus KE. At the end, it's only kinetic energy. Correct? So it's like you have two bottles. Initially, the bottle with the potential energy is full, bottle with the kinetic energy is empty. And slowly you are filling up the kinetic energy one, and the level on the potential energy bottle, it decreases, and the level in the kinetic energy bottle is rising. At the end, potential energy bottle is empty and the kinetic energy bottle is full. Right? But the total energy remained the same. Right? You didn't get any external energy from anywhere else. However, we know that when the roller coaster moves, there will be friction. We have ignored friction in this particular problem, but if there is a friction, it goes into the air. So there will be some work done against the non-conservative forces. Right? If we start considering them, then we may not end up getting the same answer that we are getting here. Probably the velocity will be lower than what it is right now. Because all the potential energy, some of it would go into the heat or doing some work against the friction. Some would go into the kinetic energy. So the kinetic speed cannot have the same value as this one. It will have slightly lower value because of being wasted on the way. So if there is a non-conservative force, how do we take care of it in the equation? Is this example clear? Let me tell you one thing. These examples that we go, the strategy which is used, I'm not talking about anything specific to the roller coaster. I'm saying the strategy, comparing two energies. This is what is going to be for this chapter problem. Always. Okay, you are going to take few points. You're going to see few points. You're going to compare their energies. Okay, and come up with the unknowns, for the answers for the unknowns. This is the basic strategy. If you start following it now, it would be easier to do the complicated problem. Give me some examples from the everyday life where the potential energy going into kinetic and kinetic going into potential. Mm-hmm. Okay. Yeah. Do you remember the lab we did with the projectile motion? How did you mount the ball on that spring? You pushed it all the way back, right? And when you press the button, the ball moved. What did you do there? You did some work there on that spring. There was a spring. I think I did mention it, at least to my lab student, that there is a spring inside. You did some work on the spring, and spring moved back. When you let it go, the spring, all the potential energy goes into kinetic, right? The clocks, the spring clocks, where you wind the spring and it keeps moving the needles for a long time. There are several examples. One example we just used in the amusement park, the roller coaster, the kinetic energy and potential energy. In the car, potential energy stored in the bonds in the form of the kinetic energy. When the fuel is burned, that is released. That goes into the kinetic energy of the tire rolling and the motion. So most of the problems that the car example is not specifically the mechanical energy. It has a lot of energy, chemical, heat energy involved in it too. But mechanical energy, pendulum moving, you attach something with a string, let go, it's constantly potential energy, kinetic energy. So you pull the spring down, moving up and down, constantly potential energy and the kinetic energy. Okay, so the everyday life is full of these examples which involve the mechanical energy. By the way, the sum of kinetic energy and potential energy, these all together are called mechanical energy. Energy of the machines. Okay, the word machine. So it's related to motion. Machines move, and when they move, they will have some sort of potential and kinetic going in there. If the non-conservative forces are involved, so I'm taking you back to the formula that we had here, delta PE negative plus W non-conservative delta K. It's one of the formula that when I started the class today, after a few lines, this is what I have on the board, where I plugged in the work done by the conservative forces. Right? This is something we did today. Work done by the non-conservative delta KE plus delta PEG. So if there is a non-conservative force, instead of setting this thing equal to 0, the work done by the change, the work done, or you could say the change in the kinetic energy and the potential energy would appear as the, I can further simplify it actually. We can do force times the distance, the non-conservative force, or it could be friction force. All right, is equal to delta KE plus PE. So whatever is the change in the total energy of the system, that would be equal to that would be used to work against the friction. Or this is the same thing I said, some of the energy would go into doing some work against the friction. Negative. Or delta E yes.
What does the FR stand for?
Friction.
Okay.
FR is for friction. I have actually put the force there. But this force could be different force. It could be the drag force. Then you're going to have to use the drag force formula there instead of this. But if it is, the most common one is the friction force, dealing with the solid objects' motion on each other. Like I already said, potential energy due to gravity is not the only one. Any questions so far?
So is delta E equal to negative FR times
Displacement, the right hand, the left hand side remains the same. I just replaced this by the total energy. Elastic potential energy. That's the other kind of potential energy that's related to the object being potential energy related to the object being stretched or compressed So the potential, because that will change the position too, When you are stretching the object, you are changing the position. When you are compressing the object, you are changing the position. And that is also a potential energy, but related to the elasticity of the material. So for example, if you have a spring, we often use the example of the spring. However, this force is related to all objects, but springs are easier to stretch or compress. So if you have a mass attached with the spring, and it is at some initial position, when you pull it down to a new position, let's say this position, it is final position. That is its equilibrium position where it's normally going to be. But if you pull it down, it goes to a new position, and you have stretched it, right? You have stretched it to a new position. What happens when you move the force away? What happens if I take my hand away? The spring would go back up, right? This is our common observation. But does it go back up without any force acting on it? But what force? Do you know that is a special force? That is the force we have not seen so far. It has a special name to it. It's called restoring force. That's mostly related to the stretched or compressed bodies. That restoring force is defined as, it was defined by Hooke, scientist, and it's called Hooke's law. He said that this force is proportional to stretch produced. Okay, whatever is the change in position, and this is that. So in more is the change position, more would be the restoring force on that object. And he said something else about it too. He said that there is something about the spring which is controlling it. Some springs are just too difficult to stretch. Some springs are just too easy to stretch. So what is so different about these springs? The spring constant. That K value, this is called stiffness constant. This is called, also called spring constant. Okay, in some books I have also seen it written as force constant, but these are all talking about the same thing. This tells you how much force is needed in order to move the spring. If the spring has a very high spring constant, it's equal to F over Y, or displacement. That's going to be Newton, 1 Newton over 1 meter. So that tells you if 1 Newton force is applied on the spring, and the spring has displaced by 1 meter, the K value will be equal to 1 Newton per meter. Okay, so if obviously if you have 1,000 Newton per meter spring, that means you need 1,000 Newton force on that spring to move it by 1 meter. It must be a very strong spring. Okay, the springs used in your cars, they are very hard to move. They require a lot of force. The springs which are used in your garage doors, they must be very strong. If you have a small spring constant, 50 Newton per meter, that means it is the one which would be displaced easily by the force. It should be a very light spring. Also, there is something missing in the equation. Okay, I'm going to add it. So your equation, Hooke's law, is not complete yet. Does anyone know what's missing? Think in terms of direction. When you have displaced it downward, which way the force acts? Up, very good. So when you have displaced it, when delta y is down, force is up, right? When it comes back here, does it stop? No, due to inertia, it's going to go to this position. And at this position, how about delta y? Is it positive? Yes. right? It's upward. What about the force? Which way the force will go? Down, because force is always trying to bring it down, right? So force is down. Does displacement and force always opposite? Are these forces always opposite? The displacement and the force always opposite? Force and displacement always opposite? Yes. A negative sign. Okay, now Hooke's law is complete. This is called Hooke's law. This force has a special name, like I told you, restoring force. Restoring force means it's trying to restore the original condition of the object. It could be in the shape, it could be in the stretch. Okay, it could be in the length, it could be in the shape, it could be in the volume, in any form. This restoring force is there just to maintain or bring the object back to the same position. Or the other way to say it, the force is always directed to the center, to the equilibrium position. Okay, one way to say it, force is always opposite to the displacement. The other way to say it, force is always pointing to the center. Was it always pointing to the center? I erased the picture, but was it always pointing to the center? You can look at the picture you drew from the board. Yes, it was. Okay, because its intention is to bring the object back to the equilibrium position, natural position. The total force, average force on the object on the spring is where it is. Oh, I erased it, but I needed it. So, okay, I will redraw it, but I'm going to draw it this time on the flat surface. So I have object sitting here in the natural position. I have stretched it to a new position. It's delta y. I have two positions here and here. Here the force is 0. Here the force is negative kx. Here also when it comes back at this position, the force is also negative kx. So on average, the force would be equal to 0 minus kx over 2 or half kx. So on average, the force on that trip, because minimum value is 0, maximum value is negative kx. So on average, it's going to be half kx. So total work done by the force would be equal to force, restoring force, which is force average into distance, half kx. If it has displaced by this position, initially it is at 0, later on it is at x. If it is displaced as x, negative, w is equal to negative half kx square. So if we are using two random positions, the total work done, if the spring has displaced from xi to xf, two random position, total work done by the force would be equal to negative half kxf square minus half kxi square. This quantity is called elastic potential energy due to spring minus elastic potential energy at position, final position, initial position. Or we can also write it as negative delta PES. change in potential energy of the system is equal to the work done by the spring force. Okay. One last line, okay, leave it with that line. Potential energy due to spring is equal to half kx square. Okay. We will start from this point in next lecture. Okay, we will move on. I have introduced all kinetic energies and possible potential energies so far. Now it's a problem time. Okay, I'm going to do some problems with potential energy, kinetic energy, potential energy, elastic, and the gravitational or kinetic energy. Okay, all of them combined in one problems. All right, I'll see you on Monday. Have a good weekend.